So, well, if you recall what I was trying to, no, sorry. Well, I'm ready to go. Okay, so welcome to the next lecture on the micromechanics of exercise media, and I just forward my notes to make sure. Don't forget it. I think pretty important. Okay, so when just to again provide a bit of context to keep updated. So basically, what I was spending most of the time, or all of the time last week, and also the week before, with this notion of so-called apparent properties, because which is a name coined or terminology coined by Hue in 1990. So basically, the thing is that if you go through this averaging based definition of homogenized properties, that actually it turns out, and it doesn't matter whether you will take this PD approach or variational approach, that in order to work with finite size bodies, you also need to take into considerations the boundary conditions. And this was the reason, or understand it properly, basically for that purpose, I have just talked a lot about this orthogonality. And again, I would like to recall, hopefully for the last time, that there are two fundamental types of fields we need to take into consideration. One are constant fields, and the complement is are just fluctuation fields. So this is the first distinction, and the second distinction is this divergence and curl-free fields, which, and the trick is that these fields in a certain sense are orthogonal to each other, and by that orthogonality, they actually live in different worlds, basically. So there is no way how to compensate for a constant function by something which is fluctuating, and there is no way how to substitute or compensate for the divergence-free function by curl-free function, for instance. So this is the structure which I was talking a lot. I'm still talking about. So the other take which I actually just raised is that it's when I was trying to make this argument, it actually turns out that this is not universally valid. The thing is that actually, in order to ensure this orthogonality, I need to take into account the boundary conditions. So this is where these two arguments actually become connected. And I was trying to put forward that actually I have two versions for finite size bodies in which I have these compatible fields, but derive from a potential or displacement field, if you would like to see it in this way, with zero boundary conditions, and divergence-free fields with no extra condition. And these are just this is the second counterpart, meaning that here I'm working only with the compatible fields, but no additional boundary conditions. But to take the obtain the full space, or to get the complete information on board, I need to consider the fields which are fluctuating. This J means that these are divergence-free and they satisfy this uniform insulation boundary conditions on the boundary. Okay? And why I was so obsessed about that is that actually it can be shown, at least in one direction, that this question whether the data determined by homogenization, whether they coincide, actually boils down to testing this orthogonality. And again, this is something which to experts is known, presumably. At least some of the referees claim that, but for us it actually took some time to think this over. And there are multiple versions of the results. Okay, so now how it aligns with this homogenization story. So this is this picture, which is my invention, which means that it is a very complicated way how to explain many things. Tries to show is that actually there are two types of homogenized properties in this viewpoint, which again to honor this Hewitt inside is something which I will call apparent, and it is actually somehow related also to this four-component scheme I was talking about, because I can either have a look from the viewpoint of primal or dual formulation, irrespectively whether this is variational PDE, because these are equivalent. And I also will consider this uniform Dirichlet or Neumann-Papel boundary condition in the sense I have reintroduced. And it actually turns out that if there is this horizontal arrow, then these two problems are completely equivalent. So it's up to me whether I would like to solve this dual or primal version. They will just give me precisely the same output. There is no difference. And if I have these two fields again connected by the dot, then again, these two are basically equivalent. So again, it doesn't matter whether I will solve primal or dual, these are the same. So one immediate consequence is that this is good news in a certain sense, because the primal thing is something which can be reasonably well treated with the finite element method. Which is something Martin particularly will heavily build on in part 2. So it turns out that in order to get these all apparent properties I need, actually the only thing which I need to do is to be able to solve this primal problem with zero mean condition, and also with this Dirichlet boundary condition for the fluctuations which are equal to zero, and this gives me this full range of properties, apparent properties I can get. And how I know that, then again, I'm really sorry for making this obvious argument a bit misleading again, is that now I will put on my variational glasses and to understand how these four quantities, out of which two only are independent, because then I can actually put forward this equivalence condition. In order to understand how these things are ordered, I actually can state that via the definition, this is what defines my homogenized apparent properties by some minimization problem. And because these two spaces over which I'm performing my minimization are ordered in this particular way, so in one case I'm solving this minimization problem over some functions which satisfy some additional conditions compared to the second case, that actually it can be shown that this condition holds. So these ones in which I have some conditions prescribed on the boundary, in a certain sense provide an upper bound to this apparent properties. And this is basically what one gets. And again, I made this argument in a very stupid way, and I do again apologize for this. But actually, then it turns out that by this equivalence, I can just make this full argument. So here, actually, I lost quite some time, because this is a transition which I can make easy. The problem is obviously that this is, as far as I know, a way of explaining things which has not been written in any of the standard textbooks. So I need to make the argument by myself, which is always more difficult to construct. Okay, so this is it. I also said that there is some discrepancy between these two, which actually leads to conclusion that these are so-called apparent properties. These so-called apparent properties depend on two things: on the sampling window or the domain over which I'm performing my averaging, and also on the boundary conditions, which I will choose either in my real or some virtual kind of experiments. And why I actually am so disappointed by this is that if something depends on size and boundary conditions, I cannot say that this is material property. So this actually boils down to the last notion I need to introduce in this course, and this is something I would like to focus on in the remainder of the course, are so-called apparent properties. These are obtained formally by actually saying that I do not want to have this I do not have this property. So I do not want to have this difference, this duality gap. I would like to actually squeeze it to zero. If you just take the argument I have just presented now and go in the opposite direction, it can be traced, this discrepancy can be traced back to the fact that there are two ways how to split the space in terms of this orthogonality. And it turns out that if I would like to have something which can be called material property, I have to have only one way how to split the space of the functions with finite energy. So in this particular setting, oh sorry, I have just now realized that one really weird construction from the literature now starts to make sense to me. So this is my internal note only. Sorry, otherwise I'm able to forget it by myself. So there is some space which was introduced by one of the luminaries of the field. And after many years, I perhaps understood eventually why this is the case. But anyway, so in this case, it actually turns out that the only way how to get rid of this discrepancy is to take formally the case in which my domain of observation is infinite. So there is no boundary, hence there is one split in place. And this is something I would like briefly to comment on. The final thing or the remark which I wanted to make, but I was already taking too much of your extra time, is that there is also one and second case in which, again, there is no ambiguity in understanding what the homogenized properties are. And this is the case in which the material or the medium they possess some periodic microstructure. So here the thing is that I have a certain cell in question, which I will call capital Y in the follow-up course. And basically the assumption there is that whatever is contained here actually gets copied in the horizontal, vertical direction and 3 dimensions also in the third one. So if this is the case, then actually everything then can be formulated in a way that there is also a unique definition of the effective properties. But I'll talk about that in part 2 if you will decide to enroll also this course. So this is the end of my part, and then Martin Doshkar just comes with his point. So what I wanted to say that in order to get rid of the finite size dependence and get genuine material properties, there are basically two ways how to get rid of boundary. One is assuming that I'm analyzing infinitely large samples, which is the case I'll consider now. And the second option is that I will restrict myself to this periodic case in which, again, there is no boundary, basically, because everything repeats infinitely. I'm just basically taking this sample and I'm just tessellating my space. So this was the suggestion. So sorry, this was just the summary of what we did before, and I have the final bit to explain to you how actually this is to be interpreted and understood in terms of some potential applications. Because, honestly, I have not presented something super concrete now, and things now become really awkward in the sense that now I'm trying to convince you that to have some effective properties, some material property, I should be able to do sample testing on samples which are infinite size, which is something which doesn't sound to be very appropriate. So just to give you an idea what I meant by the previous thing, so you can imagine, or the mindset is that you have here some background microstructure, and this background microstructure is actually defined on the full space, so on my RD. And there are still some data which are either stored in this L of x or M of x, doesn't matter. I have still my coordinate system, x1, x2, again, I will consider these two cases where the body is subjected to this a bit non-standard loading in terms of this mean gradient type of quantity or mean flux. And what these all things mean can be best explained by taking a sequence of these observation windows. So what I mean by this is that, I will take my distribution of material properties and I will sample it first using some sampling volume which I will call, for instance, omega 1, but you can call it as you wish. And sorry, just to have it more aesthetically pleasing, I will actually use superscript here. So what this means is that, I know from the previous considerations that in order to characterize the response for this snapshot of my microstructure or for my sampling volume, the only thing which I can do is to take these two extreme homogenized data, either in the primal or dual problem. So I will just go for that primal viewpoint. So I will have this L apparent because I'm working with finite size domain. This will be given for my domain omega 1 and Dirichlet boundary conditions. So sorry, actually, that superscript would have been a bit more aesthetic. And then I have this counterpart in which I'm solving the same problem, but I lift my boundary conditions. So I will have this L apparent omega 1, right? So these are the two data. I do not know whether I explain it really in a very convincing way, but if you just try to follow my argument and be very careful, it actually follows that this is the full range of the homogenized properties I can get. And there is this relation, which is something that I would like to write in this particular order, meaning that apparent properties with homogenized Dirichlet boundary conditions, there are an upper bound, but in the sense of this eigenvalue, so in the sense of energy which is stored in that homogenized medium. I really did my best to try to give you a glimpse at least what this means. Also, because of this duality principle, and arguments developed, for instance, by Ivana Pultarova, now I know that this is also equivalent to this dual apparent properties on this finite size domain with now perfectly insulated boundary, but I just need to invert it. And I also can write something like that on the top. This is not so much important. Okay. And then what I can do is that I will take this observation window and I will introduce this to the second sampling window in particular. So I will have the second mind experiment run now on this finite size window omega 2, which will give me yet another set of homogenized properties, which in general actually are in no relation to what I was showing before, right? And again, I can say that these are equivalent to this dual coefficients, but let's keep it for the moment. And now I can proceed with this line of inquiry to actually define some, or to say that I will construct my apparent properties for some omega I, where this I goes from 1 to 2 to up to infinity, or up to 1, 2, and keeps increasing. And here I will use this Dirichlet type of boundary conditions. Here I will have this L apparent of the omega I, but with no boundary conditions. I'm assuming that I'm taking larger and larger samples, which basically means that this omega I is always strictly contained in the next observation window. So these observation windows are nested and are increasing. So what I can eventually show that these two properties will converge in energy. So in the same sense as I know that these are ordered to this effective properties of my material. So this is something which can be even rigorously shown for very general media. So these arrows, this is just standard definition of convergence. And I do not know whether you recall that, it has been some years when you heard it, but basically if certain sequence of apparent property, certain sequence converges to some limit, it actually says that if I will pick some accuracy with which I would like to approximate that effective properties, there is some, in this particular case, some finite size observation window, which if I will keep increasing, then actually I will be close, I will be sufficiently close to the target value with the prescribed, accuracy. If you do not know what I have eventually meant by this, then just forget it. Perhaps for that I should have prepared some brief summary what convergence means. So actually it says that these effective properties are some fictitious quantity, but it is a quantity which can be attained by sufficiently large observation window or my sample I will be testing, right? So this is roughly the idea. So again, this is how you should understand this effective, so meaning that this represents some homogenized properties which are for the observation window or the sample size, which approximates these properties with a preselective accuracy. Okay, so again, still not very useful, I'm afraid, but I'm almost there in making the final argument. Again, I would like to make some remark which actually says that this goes to some considerations which are actually done much earlier. So there is one of the cornerstone articles in this Mechanics of Heterogeneous Media, or Physics of Heterogeneous Media, which was given by Hill in 1969 in then established journal, which is called Journal of the Mechanics and Physics of Solids. And in my role, this is the best journal in this particular field. And in that journal, he introduced something which is called representative volume element. Which, if you just have a look at it, and it's a very nice paper, you will actually be able to see this kind of argument. So this representative volume element is actually this observation window omega I, or the sample size, if you wish, which is sufficiently large. So he was not really specific about this, but using the duet kind of approach, there is a way how to make it rigorous from the engineering viewpoint. And interestingly enough, actually, this is the setup which also is able then to be used in mathematics and prove it in standard sense. But this goes beyond my knowledge in all honesty, and I don't think actually there's a person in the Czech Republic who currently does that, except perhaps for some people who are working on this for fluids. But this is, something I'm not brave enough to try by myself. Okay. So now, how to, understand how this all eventually fits together, I need to present the final part of this very long lecture, which I decided to call Principles of Upscaling or Homogenization. Principles of upscaling, or also the term which is nice and I like it is so-called scale transition. And the argument which was a bit visible from that motivation lecture, particularly from this numerical part, not so much actually about this in this Maxwell, Riley, Einstein type of relations, is related to the fact that my ultimate goal in this whole homogenization business is following. Or my ultimate model, if you would like to call it in this way. So basically, the thing is not so different from this variational approach to homogenization. So what I'm eventually after is the following mind setup. And now I need to be, more careful about notation. So this capital M, this is something which I call macroscopic in this particular setting. But I'll come to, yeah, this will be completely irrelevant in part one, after I will make my argument, and it will be of some relevance in that computational part of that follow-up course, but we will then, of course, repeat that. So basically, if I would like to understand what this macroscopic means, this is my viewpoint of engineering analysis, right? So this is the viewpoint in which, if I would like, for instance, to analyze this structural element, I will just pretend that this is something which is the constant homogenized properties everywhere. And I will claim that these are the material properties. So from this very long line of argument which I made, here I would like to analyze my problem, and for the material data, I would like to use this effective properties. And then, I have basically the setting of what I was talking so far, in which I will have this omega with no superscript. Here I will have my L of X, my heterogeneous distribution of material properties. I have independent coordinate system. And I said that actually, in order to have this material independent, I need to consider actually the case in which this is not finite size, but infinite size. So this is something which is called, again, in my jargon at least, macro scale. And sorry, I'm just missing the proper word for that, but this is, the viewpoint of, I will call it nerdish, but I don't know whether this is the proper adjective to that. So I mean, this is just a problem I will focus on in this course. So this is the part of analysis in which I will be very much interested in solving this infinite size problem with some distribution of my coefficients, and this is something which is called micro scale viewpoint, in which I will again have a look deeply into my microstructure, and I would like to try to understand how the basic data I can have about the microstructure actually can be translated to this L effect. And again, this is something which people doing genuine engineering analysis will never have to consider. Basically. So now the thing is, that I need to make these two viewpoints somewhat coherent. So if I will have just some macro scale problem, actually what I would like to get from my microscopic problem is nothing else than to be able to send here this capital E, which in my interpretation actually can only depend on this macro coordinate, right? So this E is just representing some gradient type quantity, strain, for instance, or intensity field, but living only on the macro scale of the engineering analysis. So this is something I know from my previous courses of continuum physics, independently on the relation I will get. And I would like to, my subscale analysis, just do the only thing and return to me this macro flux or stress-like quantity, again, for a given point of interest in here. And actually, I would like to have this quantity only varying at the level of the engineering analysis. I would like to disregard this part, which I do not want to know in the engineering analysis. Okay, so I was talking a lot about the micro-scale problem in very different contexts. Even I'm not so cruel to repeat it over, so I will briefly comment on how this macro-scale problem looks like. So if I like to have a look at it through this variational glasses, in this 4-component diagram glasses, which I do, then actually, I have some quantity, which I previously called U, so just to keep it consistent with that notation, I will call it capital U, but you can call it as you wish. This is something which depends on this macro domain position and nothing else. So it can be displacement, for instance. Then I will have the quantity which I have already introduced, which is this capital E in the macro point. I will have this macro flux, which I will call J. In a given point, and here I will have some intensity Q, which again I will assume that actually the only thing which matters is how it varies over that engineering scale. I will not assume that this is something which happens too fast in the micro problem, because in all cases I actually said that this is zero, so I'll try to justify it in a minute. And it's a bit embarrassing because I was updating the Google Space for this course, and only to find out that actually I already spent 3 lectures when trying to actually arrive on the fact that if I will just make this whole argument complete, I know that I have this primal and dual homogenized coefficients that are completely equivalent, so I can do it in one way or another. In the macro scale problem, actually, again, it is more customary to work with these quantities. So basically, it means that I can go from my primal unknown U to that intensity or gradient-like field by taking conventional gradient. But I need to be careful because now that the gradient are derivatives, I have 2 coordinate systems, so I need to be nice to, nice to my explanation to say with respect to which coordinate I will be taking the gradient. So with respect to this coordinate system, because this is macro scale problem. Okay, and here again this is related. Sorry, that there should be this minus again for aesthetic reasons. And here I will have that micro divergence. So last year I explained it a bit different, but I think this is just equivalent. Perhaps. Okay. Plus I will add, standard boundary condition. Or if I do not like this PDE approach, you know, I can also take this variational viewpoint. But for that, actually, I can recycle all the knowledge which you learned from Milan's courses related to universal principles of mechanics in any version it has been offered, right? So, I mean, if I would like to understand how this is to be interpreted from the point of view of variational principles, then this is precisely what Milan did. So, I can now repeat the same story or better skip that. Okay? So it's completely equivalent, so it doesn't matter. And just to fix the terminology, this is again my primal potential. Yeah, I see this non-symmetric. This is my primal intensity field. My macro potential or macro displacement in the case of elasticity. This is my micro intensity. This is my macro or engineering or whatever flux. And this is my micro source field. So perhaps, you know, not very transparent argument, but the argument which I wanted to make in the best way I can is that this part in here, this should represent something which is rather standard. Because I'm solving, you know, the type of model I'm used to. The only thing how these heterogeneity is taken into account is through one or this coefficient or that coefficient, but because I have this size independent properties, and this is why people like myself are so concerned about that, then basically, again, I'm just solving my conventional engineering problem, but with some data which are determined by some subscale problem, right? So basically, this is this justification of you know, using, for instance, some models of elasticity and isotropic elasticity in particular for analyzing, let's say, wooden structures, because these anisotropic coefficients, they reflect the microstructure which is beneath, and this is precisely what you do, right? So this is basically the story. So this is what, again, as I told you, this is my ultimate goal or mindset. And this is something I would like to you know, understand and do. And this is also the justification why actually this makes at least to some sense. But now, you know, I need to take this into account in a reasonable manner. So basically, this is the setup in which I actually can post my final analysis, at least conceptually. But of course, this is not something which is universally valid. So now, you know, I need to take into consideration some modeling assumptions. So again, this is something which is not always true, but if it is true, this is proper model with which I can work. And again, I can attain the fact that I can just reuse everything I have been told in my previous education, except for the fact that I will need to change my coefficients to something else. And for that, usually the argument which is usually taken in consideration, which is something which is called scale separation. And this scale separation can be best explained by introducing three length scales. So basically, there are three length scales involved. One, so this is my variant of L ladder. So there is one length scale which I call L, Then there is another length scale which is called E. And then there is one length scale which is called L, macroscopic. Okay? So now, to which part of this scheme is this actually associated? So this L is something which in the jargon I'm very much used to. This is called micro length scale. And this is something which is related to characteristic variation of my data, of my coefficients. So this is something which is related to the characteristic size of my microstructure. So for instance, my aggregates, or if I'm a concrete person. Etc. Right? So this is one long tail which is in question. And for instance, in these fibrous materials, the usual, roughly the size at which I can measure it is in the order of micrometers, for instance. Right? Then, of course, there is the second scale, which is actually characteristic of that micro problem, but actually it turns out that what is really not so important is how that macro domain looks like for this argument I would like to make, but actually is related to the characteristic size of the variation, but not variation of this primal quantity, but variation of this E or J, if you wish. This is equivalent, right? Because these are just local properties in that understanding. So, in the argument I would like to make, these two are just fluctuating in the same way, because this L is constant. So if this fluctuates with respect to some length scale, or changes, on certain length scale, then this just needs to follow. So again, this LE is actually something which I do not know how to call, but this is just the scale of variability of macro fields. And then there is this third scale, which is now related to the size of my macro domain. So this is something which gives me the idea how this omega n is, right? And now, to have this model correct, and I hope now this argument is complete because I refined it several times. So one thing which you need to actually make sure is that this L is actually substantially smaller than LE. So these two inequalities means substantially smaller. And why I need that is actually that if this L here, so this characteristic variation, is by many orders of magnitude, or several orders of magnitude, smaller than the scale on which this quantity varies, then if you recall, actually, here, I was assuming that I have my microstructure subjected either to capital E or capital J, but these were constant everywhere. So these were vectors, which means that they are constant, but they are constant in this omega, in the macro. Right? So if this assumption is to be valid, then actually, if I just do this kind of transition, then I need to make sure that the change over which this macro problem actually happens must be okay, so this is one condition. And the second condition is related to the fact that this capital yeah, well, I have it. No. Yeah, I'm sorry. Yeah. So it's perhaps good news that yeah. Oh, the argument is finally complete. Yeah. So I do recall that I have some doubts, but I didn't write them down. So, sorry. Well, actually, to make this argument proper, then actually this Lm, a bit illogically, is actually the size of my observation window. So what also must be, so this is the scale or characteristic size of my finite size observation window. And for that, I need also to have the inequality that this L, this characteristic microstructural size, is substantially smaller than Lm. And this actually says that my observation window is sufficiently large such that actually these apparent properties become really the material property. So this L over Lm ratio must be substantially smaller than 1, if you would like to call it in this way. And this actually is the assumption which allows me to say that my apparent properties actually converged with given accuracy to my effective ones. So again, the size of my observation window must be sufficiently large in order to get this apparent property. So I think this argument can be sharpened a bit, but I cannot see it at the moment how. But anyway, so what I mean by this is there are two conditions under which I can use this viewpoint. The first one is that I have fields which on the macro scale which do not change drastically and drastically means that it will change at the length which are comparable with my microstructure. So this is one condition. And the second condition is that actually the sample from which I have derived my effective properties is sufficiently large such that I can actually substitute these apparent properties with these effective ones. So it means that I'm analyzing something which is called representative volume element. So again, my observation window, the window which I use to analyze my effective properties, is actually substantially large in order to be able to determine this homogenized part. And these conditions just must be satisfied simultaneously. So, and in that logical sense that both must hold. So again, I need to have a sample of my microstructure which is substantially large to get rid of the effect of the boundary conditions. And I also need to solve a micro problem in which this doesn't hold, right? So two things in which these, so two examples, again, just to finally conclude, where these are violated. So I will just now write it in dimensionless format to make the arguments similar. So the first typical example of the problem where the first condition is violated is the following one. It is also true in the in thermal case, but in elasticity, this is something perhaps you have better notion of, which actually means that if I will be analyzing a configuration in which there is some sharp notch, for instance, and again these are just examples. Okay, so it is known from the behavior of or for solution of field equations that actually both fields, but in particular this gradient with respect to the macroscopic variable of u in this particular case, and also the flux field or stresses, so they exhibit singularities. Right? So it's known that according to theory, if you believe this model, actually the stresses and then strains, they can be arbitrarily large if this crack is just mathematically sharp. Otherwise, there is this increase of, so this is one thing in which you cannot use it. The second one is that, for instance, if you are in a really close vicinity of this boundary, then again, there is something which is called boundary layer. And boundary layer actually corresponds to the fact that there is, very, very concentrated vicinity of the boundary in which your solution changes substantially. So again, in these regions close to the boundary, using this homogenized coefficient may be questionable because you do not have this set up, right? So this is one thing to keep in mind. So for instance, if you would like to check the quality of your solution, you can rely on your homogenized coefficient somewhere in the interior, far from this possible features which make the solution. And again, I will try to repeat, particularly its gradients. to make it really something which varies very rapidly. And by the way, I also did my short in that, but using some relatively solid micromechanical principles to describe how the crack would propagate, taking into account heterogeneity, which occurs on a substantially smaller land scale. I don't believe we still know how to do it exactly. So that there is a lot of heuristics, of course. But, to me, it's still something which is not resolved. Also because there is now some dispute how to even model the crack propagation in this homogenized setting properly. And the second one is a bit easier to explain. So if I would now be interested in the case that if I take the second ratio and take this RLM, which is the size of my homogenization window, so if this is not valid, is substantially larger than 1, so then the example which actually is used in that Huat's paper is that you are making some structural tests, and again, this will be my naive drawing, and here, you have some aggregates which are of this size. So these are some aggregates. And this is now my omega, my testing window, if you wish, either in the physical sense or in the virtual sense of solving the equations. So in this particular case, what happens is really dominated very much on the behavior by the what happens in the close vicinity of the boundary. So if you have some hard particle, for instance, adjacent to the boundary, this is different than if you have it farther. So if you just shift your microstructure, its behavior will change, and hence, the apparent properties are not really homogeneous. So this is just an example, and yeah, sorry for my childish drawings, but certainly you can find some additional experiments. So in this case, indeed, you should somehow take into account that you are not using homogenized, you are not using effective properties, but apparent ones, and at minimum you can get these apparent values solving by these two problems, or performing these two types of mind or real experiments, and this is something which gives you roughly the range in which your homogenized response, your apparent response will eventually be located. Because just your observation window was not sufficiently large, so there is certain uncertainty, if you would like to put it in this way, in your properties. Okay. And that's the best explanation I can do at the moment. Oh, do I have this handout? No. Yeah, so in these handouts, which I will then just, the PDF, I will supplement this particular notes. So, yeah, sorry, one argument which I wanted to make that again, in that homogenization business, I would like to reiterate that this is something which is corresponding to some easy problem to solve. Because again, eventually if you homogenize, you are just treating with your model. So again, if you would like to analyze some cross beam, some wood beam, then you will not delve in the microstructural details unless you are a real researcher. You will take some average properties of that, which are anisotropic. That's pretty much it. Okay? So this is something you suppose how to do. So the whole business is actually trying to solve that problem of apparent property, effective properties for infinite size domain or for periodic cell in part 2. And you know that if these two assumptions are reasonably satisfied that what you are getting makes sense. If not, then actually we are just using your model beyond the applicability. And just to, again, give you a bit of historical perspective, so these considerations were actually first put forward to this Hill's paper from 1959, and because I didn't print it out, and, you know, this is, there is some variability in this year. Perhaps this is 63, I do not recall anymore. But it actually turned out to be a very important paper. In that, actually, I will refer to it just also in the following lecture. Then there was this Hewitt kind of argument in which he introduced this notion of apparent properties and made these arguments by Hill, which were a bit heuristic, a bit more quantitative. So here, among other things, this term representative volume element, representative volume, appeared for the first time, as far as I knew. And Hewitt is the intellectual father of that notion of apparent properties. And actually, around the time when I was also working on my, I was already a PhD student, and actually paper by Samuel Forrest et al. And collaborators appeared. It was 2001 or 2, no, 1, because this was the first genuine citation of our work with Michal. We did during my diploma thesis, and he made it into very nice computational procedure. So they also do it for random viewpoint. I will also touch upon that. And the argument is really nice. They just, you know, by actually taking this samples of increasing size, they try to get this sequence of apparent properties, and from that they would just like to extrapolate this infinite size limit and make it really a computational procedure. And actually there is also a very nice paper written by Martin Doškář. I think it was 2019, where this is done in a very transparent way of having the microstructure represented by something which is semi-deterministic and semi-random. But again, if you would like just to actually see our way of thinking about the problem, then I can just highly recommend this paper. Martin also used this as a basis for this. So this was some kind of unifying viewpoint we were able to get after some work. So this is CTU viewpoint. Okay, so sorry, this was a bit longer lecture. Perhaps I should have split it into 2 parts. But unfortunately, I do not know how to make this argument shorter. I tried that, but always I'm missing something. So, to the best of my knowledge, this is just a proper way how to explain things and how the structure of the equation actually reflects in that interpretation of homogenization, interpretation of the homogenized coefficients, and the scale separation arguments, which again, they actually involve these 2 scales, which needs to be substantially far from each other to be able to use this infinite size approximation and make sure that it makes some sense. Okay. So that's it for this for this part. And in the remaining 20 minutes or so, I will just move finally to something which can be used, but where I was, so I will first start with something which is called, in the terminology in which I was educated, which is called elementary theory of effective properties. And I will just try to put forward two basic methods how this can be applied. The first one is so-called Voigt-Royce estimates slash bound. So Voigt/Royce estimates bounds, in which I'll try to convince you that although the whole framework which I have just introduced to you is a bit of overkill, may seem to be a bit of overkill, it actually allows us to really understand some methods which were developed independently and eventually to understand how these are related in very, very straightforward way. And then the part which I will start, if I'm lucky, is being able to analyze something which is called laminates, which is one of few cases in which we can solve these field equations exactly. So this is exactly solvable geometry. And again, this is the jargon I'll try to explain. Exactly solvable material, I don't know what to call it. Okay, but before doing so, I will just narrow myself a bit with in terms of the classes of materials I will consider. I mean, the restriction is at this stage by no means significant. So I will introduce something which is called multi-phase composites. Okay, and the reason why I would like to do that is that I would like to make certain structural assumptions about the data of my problem. So, if you now basically recall what was the argument I was trying to put forward in the previous series of lectures, it actually turns out that well, the only input I need in order to do this homogenization under the assumption which I have explained, hopefully, is that I need to know what is my L of x or my M of x, right? So this is the only input which I can eventually then take and convert it to either this L effective and M effective, and I have that. And again, doesn't matter which one I will take because these are completely irrelevant. Okay? So this is the only input which I will eventually need. But now if you start thinking about that, actually this is something which is rather difficult to get. I do not know whether there is whether you are expected sooner or later to work with indentation, but this L of x is something you can imagine as an indentation or data which you get from this grid indentation. So you probe locally your material properties around individual points, and for each x, you will get your coefficient. So this is basically, the kind of format which this assumes, and this is something which you never know in reality because your grid is always finite size, etc. So actually in this multi-phase composites, I make my life a bit earlier, and the usual picture which is associated with that, although it's not completely instructive, I would say, but it's fine enough to make the argument, is that one nice representative of these multi-phase uh, composites is the following. So, you assume that you have certain phases. So you can separate your material into different components. And again, I have used this terminology in this example, which I started with, but this was a while ago. And usually these phases are represented by some prevailing shape. So to make the argument, I will just have one phase which will be represented by this ellipse, which I will just fill with one color, and the second phase would be something like this, for instance, which is something I will just fill with different colors. The reason why I initially started with this potato, but they make it dotted, is that actually now this is my idea of RD. So there is no boundary, right? So if there is no boundary, then actually the absolute size of that shape doesn't matter. So I will just take this. I will just downscale it a bit, just to again make this better visible. And I will create several copies of this guy. So this is something which is a bit challenging to imitate. Yeah, this is something I shouldn't have said. Sorry. So I will just, this is how I should have done it. So I will just, draw several copies of those, which should be identical. And I will do the same stuff with the second class of these shapes I have in place. So this is how it looks like. And sorry, this is just something I can safely delete without losing any information. And what I say is that I will actually associate material properties not with every point, but I will associate these material properties with a given phase, right? So I will say that all these guys who are identical here in shape, they also carry the same properties. So each of them is characterized by distinct L, that primal coefficient or dual coefficient, it doesn't matter, these are the local properties which are mutually inverse. And now I will start introducing certain notation. So these phases are actually indexed usually by certain property, which I will call R from this point onward. So I think I will be consistent in saying that this R will always be phase index. And for this particular class of materials, I will always have this R equal to 1 present for matrix. So the thing which I will get from my infinite domain if I take all the remaining phases out. And this is just 2 and 3 for this particular case. So in the jargon I will be using quite intensively. This is an example of 3-phase composite, which again consists of 3 phases. One is matrix, one is this yellowish guy, and one is this gray. Unfortunately, the nomenclature here is not really unified because some people call this two-phase component, whatever. So I will now say that each of these phases is determined by its local properties, and I will also use this nomenclature which actually says that if I will have any object of interest, so this is what this fat dot tells, and I will write here this R in round parentheses, then this is an object related to R phase. So in this particular case, this will be L1, the properties which characterize the matrix, L2, the properties which characterize this family of these shapes, and R3. And again, I know that these are just mutually inverse. So this is first thing I know. And the second thing I know is that it's already quite late because I was unable to keep my concentration to the level to make the numbers on the left and right consistent. So sorry. So this should have been 2, and this is something which has been 3. And I can list these phases as much as I can. Okay. So any questions or? So this is one object which I get in order to get this L of x or M of x prescribed, and now I have separated the phase properties, which are hidden either in this guy or that guy, from the spatial distribution, and for that shape distribution, I will use something which I will now start to like a lot, which is something called characteristic function of the arc phase, which I will systematically denote by chi because of characteristic. It will be for the arc phase, so this is what I will distinguish by the superscript here, and this will be very easy function. So it will take values from this omega, which now in my world is actually equivalent to full domain. And for each point in my infinite domain, it will just assign it 2 values, 0 or 1. Right? So this chi r at a point x can take only 2 values. So it will be 1 if this point x is located in the domain I will denote omega r, and it will be 0 otherwise. And this omega r, this is just the part of my plane or volume occupied by the odd phase. So there's easy way how to interpret that. So if I will have this coordinate system, the only thing which I need to do is to say what is my phase of interest. So let's say matrix, and I will just take my point and I will test different x's. If this position is located in this y domain, then the function is 1. If I'm unfortunate enough to visit one of these, then this will be 0. If I'm interested in the third phase, for instance, the function will be only non-zero in this domains, which are occupied by this grayish phase, otherwise this is 0. So nothing super complicated, I would say. So again, if you will work in this micromechanics things, so then if you just imagine, for instance, that you will have your microstructure represented by some colored or binary, or grayscale. Information, then the usual way how to take some basic idea of how a microstructure looks like is that you perform something which is called thresholding, meaning that you will say that, for instance, I don't know, colors or the ranges of gray in certain, the values of gray in certain range, these are just associated with one phase. You will do this thresholding and you will get zero white or black and white, bitmap, which shows you the cases in which this phase is located or not. And this is precisely the graph of this function. So this is it, nothing super fancy. But what I would like to put forward is that this is something you can also get from a micrograph. So by this thresholding, you can just basically apply to any digital kind of image to separate your picture into phases. And yeah, there are several ways how to do it. And again, depending on your field, you will use it or not. So why I'm actually, the argument of thresholding is that this is just one example of how multi-phase composites can look like, but actually the range of materials which are described by this formula or notions is substantially wider. But the whole reason why I'm writing that down is that now I have my function L of x expressed in this particle way, so I will just performing the sum of from r equal to 1 to n, where actually this n should have been capital, and this n is just the number of phases. So this is, in this particular case, the n is 3, so this is the 3 presented here. So these multi-phase composites are also sometimes called n-phase composites, as shown here, where this n is just the parameter. So in LaTeX it would be written in this math mode. So now the expression which I have is that I have my phase characteristic function in a given point, and I will just multiply it by that phase properties LR. So basically, what this formula tries me to see is that for any point x, I will just have a look in which phase this is contained, and I will just assign those values to this position, or to this particle position x, right? So if I found that this is in phase 1, I will put L1, otherwise I'll put 0. And again, I would like to, just highlight here that by that representation, I'm separating phase properties and their spatial distribution. So this is something which lives independently, and this just shows how this property is distributed throughout the method. Okay. So now, in the remaining 7 minutes, I will try to put forward the argument that this void various estimates. And, just to explain it very briefly, I would like to recall that actually, I said that if I know what my L of X is, I'm able to solve for these concentration factors. And knowing these concentration factors and local phase properties actually gives me exactly the information which I need. So now my effective properties actually are evaluated as the average of this local properties, and here I have this identity on which I will add this fluctuating part, that is A prime, if you still recall, is this fluctuating primal concentration factor. Right, so this was my claim. And the claim was that if I knew what is the average with respect of this L times A prime X, then I knew exactly what I'm after. I would like to I would like to reiterate hopefully or introduce the notation. If there is nothing in here, I'm just assuming that I'm doing this average over the whole domain. And this is again to be understood in that from the viewpoint of the previous explanation, meaning that I'm taking the values for the windows of increasing size and computing the average, and in the limit I get precisely this quantity, right? So what actually Freud did, and hopefully I was a bit more systematic. So what Mr. Freud did in 1887 was actually a very bold assumption of saying, in that terminology I have just built through the course, that there are no fluctuations because of microstructure. Okay? So no matter what I do, I will have this particular, there will be no fluctuation at all. So in other words, if I will just do this mind experiment, assuming that I will prescribe this capital E in every point in my infinite domain, this would be the solution. So this is what Freud assumed. And his claim is that this L effective is estimated under this assumption by the following object, so which is this L of X matrix wise identity matrix of corresponding size plus 0. So if I will just do the algebra, the only thing which I need to do is to average the material properties. And this is precisely which I will call L with the subscript V. And this V is because of Mr. Freud. Yeah, unfortunately, both works I will comment on are written in German, so I'm unable to read those. I don't think they were translated to English, but this was his suggestion how to estimate elastic constants of porous crystalline materials, which is a bit different from the framework I have introduced, but this was his initial motivation, so he was some kind of best. Okay, so what this means in particular, not for the setup which Voigt was interested, but for this N-phase composites, this is, not so difficult to imagine, hopefully. So this L Voigt is actually, by definition, the average over this infinite domain of my L of X. So now I will just expand it out a bit. So this is just one. So this, if you recall, was one of the volume of the domain, and I will be integrating over domain because there is no index in here. I'm again formally assuming that this domain increases up to RD and up to space, and the same thing happens in here. So this is what I was saying, that I'm integrating over the boxes of increasing size, and I'm looking at what is the limit value. So there is even a way how to write it more appropriately. That would make it too technical. So now I have this integration, the summation over R equals to 1 to R. There is this characteristic function of the R phase in the x coordinate multiplied by LR, and I'm performing my integration with respect to x. Okay, so now I will use the fact that this integral, or the averaging operation, if you wish, is linear, because integral is a linear operator. So this is then x independent, so I can just throw it out in the consideration. And this sum is also something I can throw away. And for aesthetic reasons, actually, it would be nice to put it just to the left as far as I can. So yeah, I will just equivalently write it as a sum of r equal to 1 to n. And now I will have this 1 over the volume of omega, where again this omega keeps increasing, integral over omega. So with respect to the same observation window, this will be chi r as a function of x dx, because this characteristic function is the only thing which depends on x, and this is now post multiplied by our r, by this matrix in there. So now, if you recall the definition of the domain of that omega r, this is actually something which in that integral contributes only if my point is lucky enough to be located in the position which is occupied by that phase, and which phase I'm talking about is what this outermost index r tells me about. Okay, so if I'm somewhere else, then actually it doesn't count at all. So then what I'm doing is that I'm actually computing 1 over the volume of my infinite domain. Now, because I'm a very lazy person, I actually do not want to integrate over the complete domain, but only about the part which contributes. So this is precisely this omega r, so that part of that Rn occupied by the R phase. Well, this is nothing else that volume, if you think about what is, the geometrical interpretation of this integral. But this is not the domain of the full sample, but only about the part which is occupied by the R phase. So what I eventually get is a very simple expression. It is sum of R equal to 1 to n. Here I will receive a volume occupied by the R phase, normalized by the volume, multiplied by LR. But this is nothing else than the quantity actually we have seen in that motivational example. There I a bit inconsistently denoted as phi, which was the volume fraction, but now, and I should really change that to be consistent in notation. So I have this CR, which is just, ratio of two volumes, one which is occupied by the R phase, the second one which is the volume of the observation window, and what I'm assuming that actually this number will eventually stabilize if I increase so this fraction will stabilize to some number to which this converges to, and this is precisely my volume fraction of the given phase. Okay. And this is the ratio of two positive values, or non-negative. Yeah, so this is the ratio of the non-negative value, so 0 or positive, with respect scale to something which is definitely positive. Then actually this volume fraction is always located between 0 and 1. And again, I would like to reiterate that this is not some mass fraction, this is just volume fraction, because I'm doing volume averaging. So what I get is some very celebrated Voigt formula, which says that if I would like to estimate my effective properties according to Mr. Voigt, the only thing which I need to do is to take the properties of individual phases and mix them according to their volume fractions. So this is something which is called rule of mixtures. And if I just follow by analogy, what Mr. Freud did in 1929, so it is 40 years later. So he just took this PD perspective, but dual viewpoint. Mr. Freud, is primal one. So he said that no, I know that my dual concentration factor is equal everywhere, and I will obtain my, and now you will just do precisely the same story. So you will just follow the same argument. You will get this MR. This R stands for Mr. Royce, and his final result was that I will do precisely the same thing, but with the dual coefficient. Okay, so Mr. Royce estimated the dual coefficient. So this M effective, according to Mr. Royce, can be replaced by this quantity. And this is something which is called inverse rule of mixtures. And why this is so, and how this is related to that rather extensive machinery of different notions and relations, this is something which I would keep to the next week. So thank you very much for your attention. Now I can see that I'm significantly over the 40 minutes. I do apologize for that, but we are, I do not know what to say. So now, if you would like to do a bit of homework on this apparent kind of properties, then I have already assigned the additional homework assignment, but I now realize that actually I didn't set the submission dates, so it's, so this is something I need to do after the lecture. But yeah, I'll do that so you can just have a look at it. I did my best to give some supplementary problems to allow you to think about these apparent properties. But I'm especially unhappy about this part. So if you have some suggestions afterward, what should have been done differently, then I would certainly like to know them. Okay, so that's it, and yeah, thank you very much for patiently listening. Yeah, and I will just conclude it.